So MIOX is the leader of on-site, on-demand chemistry. We also have been working in the oil and gas industry for many years with some of the biggest names in the industry. What we've found is oxidants eliminate the most bacteria, period. They do it fast and they do it effective. We can do high treatment rates, so we can recycle the most water per day. We eliminate the H2S. We can reduce the iron, which can cause scale, and we can reduce the chemicals on the road. So most importantly, we're a safer process and we're lower cost to put more money back into your budgets. On the screen right there, which is called the MIOX pen or MIOX purifier pen, it's been sold online for many years, but most importantly, it was a government contract where it was actually given to the troops in Afghanistan so that they could stay out extended periods of time without having to bring water and hike around with water. So essentially, it uses batteries, table salt, and it electrolyzes a brine solution to create mixed oxidant. And mixed oxidant is essentially sodium hypochlorite and hydrogen peroxide. So it's better than just straight sodium hypochlorite and can actually kill organisms that just straight bleach can't. So this gave some benefits to the troops in the fact that they could actually treat their water on site with no matter what the water source and make sure that they weren't going to get sick during combat situations. So like the picture shows, we take a brine solution, just regular table salt, water, and we electrolyze it between a cathode and an anode, and what comes out is the mixed oxidant solution. Now, how do we know we have something different? Well, over the years, we weren't quite sure exactly what it was, but over the last few years, we've pretty much narrowed it down to hydrogen peroxide and sodium hypochlorite. This is an example of a third-party test that or a test that was confirmed by a third party, the Center for Disease Control, where we actually treated killing Bacillus globigii spores. Now, the reason for spores is they're actually a lot harder to kill than, let's say, an SRB, sulfate-reducing bacteria, or an acid-producing bacteria, an APB in the oil and gas. Spores have a very hard outer shell and very hard to penetrate and very hard to kill. It's why sodium hypochlorite isn't used in some applications, because it can't actually effectively kill certain things. Now, MIOX, being that we have the mixed oxidant properties, we actually do a very good job of killing these spores. If you look at the slide counts there, you can see that we got it down to 16 culture forming units versus the 10 to the 6 that we had originally. So this is much better than anything like a Lysol or Contact or any other type of standard biocides that are used out in the marketplace. Better than anything a quad or a glut or a THPS or any of those used in oil field could potentially do, especially against a spore. Also, there's no way to have a resistance really to oxidants. Oxidants, once they penetrate, as long as they can get to the spore, it actually tears it apart from the cellular level, so it's not something that they can have a resistance to or over time will become resistant. Now, MIOX has been around for 18 years. We have very scalable technologies, and what do I mean by that? You saw on the second slide there, we have things that can fit in your pocket, and we have units that from a water softener size all the way up to 3,000 pounds per day. And even larger, depending on how you wanted to scale these, because they're pretty plug and play and you can put them in series or parallel. So 3,000 pounds per day, what does that mean? That means you could treat 100,000 plus barrels per day or 100 barrels per minute in real time if you absolutely wanted to. The volumes are not an issue with that much pounds per day. Now, we also have multiple chemistries. Now, this is something unique to MIOX, and why we're the leader on on-demand disinfection is we actually can do sodium hypochlorite, standard bleach. We can do our mixed oxidant solution, so hypo plus peroxide. We do an advanced oxidation where we can actually create hydroxyl radicals in situ, and we can do things like destroy some organics and benzenes and things like that in water. That's a separate technology we have patents on. We also have what we call our EQUAT, or what I like to refer to as a dual biocide technology. So let's say you have an oxidant, you eliminate all the bacteria in your water, and that water is essentially, for all practical purposes, what you would call sterile. And then, then the oxidant is consumed. Well, what do you have to keep from introducing new bacteria into that water? Well, that's where our dual biocide technology comes, is that we take a standard sodium chloride, we introduce also a quat salt, and we can electrolyze those together. So you actually have a persistent quat that can stay in the water and keep that water from turning sour from new bacteria that's introduced into the water. So it's a dual biocide technology. So many of these technologies are either patented or patent pending. We have 48 patents pending or issued to date. We've been in multiple markets for many years. We've been in municipal water, drinking water for most of our tenure as a company. We're in food and beverage. We're in industrial cooling. We're in agriculture markets. We do semiconductor water treatments, and we also do, obviously, oil and gas, and that's why we're here today. Like I said, my name is Charles Mowry. I've been in the oil and gas sector for 18 to 20 years now. I worked for a service company for many, many years, large service company, affectionately known as Big Red, for over 15 years, and have been in water treatment now for about the last 3.5, 4 years with different oxidants, not just mixed oxidant. So move on a little bit. I'd like to introduce a product line that we created here at MIOX. It's called Blackwater. Now, all of our equipment are named after some kind of body of water, and Blackwater is no different. Blackwater is named after the Blackwater River. But I figure since we always treat black, nasty water with lots of iron or H2S or something like that in it, I figure it was aptly named to just go ahead and call it the Blackwater unit. Now, the Blackwater unit, the applications for it are, we can do produced and flowback water recycling or treatment of that produced and flowback water. This could be pulled up and put out a saltwater disposal well for maintenance treatments as far as biocide and things like that go. It can be used for frac water on the fly treatments, depending on the quality of the water. We also do enhanced oil recovery water treatment, so that could be your biocide replacements or things like that in a water flood type scenario. Now, this particular trailer or this particular unit, we installed 800 pounds of, or we install 800 pounds of mixed oxidant in the unit. That could treat 100 barrels a minute, probably at 20 to 30 milligrams per liter, depending on the situation. But it handles most situations in the oil and gas. It generates 4,500 milligram per liter solution. It needs 480 volt, 3-phase, 250 amp service. For every pound of oxidant, you need 3 pounds of salt, and you need 3.5 kilowatt hours per pound of oxidant. So that kind of is the cost basis. You can pretty much figure everything from there. But I'm going to get into some of that in a little bit later in some of the additional slides. For a much larger application, let's say you had a huge water flood, hundreds of thousands of barrels per day, or you were doing 100% produced fracs of really, really nasty water and high volumes of water, then we would probably maybe even want to go up to 3,000 to 4,500 pounds per day. And that's where the Gila would come in for the next level of application. We don't see a huge demand for this size equipment. The Blackwater really addresses almost all of the market. Rigging up the Blackwater unit is actually really, really simple. If you look at the blue line there, that's your makeup water. So what we really want there is some kind of low hardness water. And if the water has an extreme amount of hardness, we can even pre-treat it with some kind of water softening or something like that. But the main goal there is to have some kind of low hardness, low scaling water, because you are going over an electrolytic cell. Then we have the electrical connection there on the right. That's where you want to put that 480 3-phase 250 amp connection in. And then essentially you want to do your dosing lines from there. Really simple rig up, rig down. Now, one of the beauties of this technology is that you can also use an external brine source. So if you wanted to, say, bring in a 10-pound per gallon sodium chloride brine, just make sure it has low hardness, we can actually plumb that in, put a tank outside of the Blackwater unit, and have the unit actually bring in the brine as it needs it. Essentially, at this point, this unit becomes almost hands-free. So there's no intervention cutting sacks. As long as it's got a water supply, a brine supply, and electricity, it can dose. And we have Allen Bradley controllers inside the unit to electrolyze the fluid and actually then dose and control all the dosing operations, and whether you wanted to put an ORP sensor, which is an oxidation reduction potential sensor, or manually dose, or some other type of parameter, for every time a truck offloads, or you want to put X amount of oxygen, or however you want to do it, these dosing pumps are capable of doing that. So I want to talk a little bit about the U.S. water supply. This is a picture I took from the USGS, so the U.S. Geological Survey. And what they did was they estimated if you took all of the water off of the globe, and hence why the globe is brown in this, is that's how much water supply we have in the world available to us. So that's the sphere over the U.S. you see. Now, how much of that is freshwater? Well, the freshwater is actually much smaller percentage of that. So how do we go about not eliminating that freshwater supply? Now, in the oil and gas, I've seen a lot of statistics, I've seen a lot of people talk about, well, we use less than agriculture, or we use less than golf courses, or we use less than this, and I would agree with that. The only stipulation I have is that, unfortunately, a lot of times in the oil and gas, we have what's called a once-through scenario. So what we do is, generally, most of you guys know this, but I'm going to go through it real quick, is that we purchase the water from somewhere, generally some kind of fresh water source, or sometimes even a wastewater source that could eventually be fresh again. We transport the water to site, then we treat it on site. A lot of times for frac, it's actually treated with a biocide. It's pumped down the well, and then the well, once it comes on to production, eventually starts putting some water back into the system. Generally, many operators, what they do is they take that water, they truck it, then they bring it to a saltwater disposal well. Sometimes it's treated with a biocide at the saltwater disposal well, and then it's re-injected, and it's pretty much gone from the freshwater life cycle that we have. So it's really, it's consuming that water source, and it's not going to return. Now, not every operator does this, and some operators are better than others, but the ideal world is that we wouldn't do this at all. What we can do is we can take the water that comes back out of the well, bring it all the way back around into the site, and then treat that water. And what I recommend, a lot of operators, or not a lot, but some operators actually do what I like to consider reuse. Reuse means they don't treat it, they just reuse the water. Now, once you get into actual recycle, where you actually treat the water with some kind of process, you can do that on site. And that's where MIOX comes in. Generally, your first level of protection against fouling your wells is some kind of biocide treatment. Now, MIOX can be, it is a biocide replacement. It can treat out the H2S if you have any H2S from that production water. It can also treat out your heavy metals, predominantly iron, oxidizing your iron out of solution from iron 2 to iron 3, so then it can be filtered. So if you take MIOX, you add a filtration step, and you ensure that your frac water has a total dissolved solids tolerance, in other words, a salinity tolerance, then you can actually reuse that water with very minimal treatment and very minimal cost. And then it can go back through the life cycle and you can keep recycling. So what does that budget look like? I'm just going to throw out some rough numbers out there. Some operators have much higher numbers than this. Some operators have lower numbers than this. But I figure I'd be conservative and just put some numbers on this. So let's say you could acquire water for 25 cents a barrel. Let's say you can transport it for 99 cents a barrel. I've had numbers up to $3 per barrel. I've seen that before. Let's say a biocide's 25 cents a barrel. That can be low or high depending on where you're at. At your saltwater disposal well, if you're treating it, it's probably, 20 cents a barrel or more to treat your saltwater disposal well. And then the actual disposing, the people, the equipment, the pumps, and everything to dispose of that water, let's say it's a conservative 25 cents a barrel. Well, that still leaves you with almost $2 to recycle, to treat water so that you can recycle it into your process. And then you're not losing that water forever in the cycle. Now, as far as how much mixed oxidant does it take to actually treat water? So generally in fresh water, you really need probably even less than 10 ppm, but I'd say no more than 20 ppm to treat that water. A Blackwater unit can treat 100,000 barrels a day at this rate, and it can do it for probably around ½ cent per barrel, depending on your power and salt costs. And this is just your OPEX. This isn't your, if you had to add personnel or if you had to add equipment, but this is your operating cost, just feedstock of salt and electricity. Now, some of the other demands that we've seen in the industry, generally if you're doing a fresh or produced water blend, you're probably in that 20 to 75 ppm range. If you're in that high demand scenario, 75 to 100, you were probably only going to treat 20 to 30,000 barrels a day and at about 3 cents a barrel. And then there's some extreme demands. And this is, let's say you had a really heavy polymer-laden fluid, oil-laden fluid, or something that just has a lot of demand. We're going to treat 5 to 20,000 barrels a day. But it's generally more economic to add some other process to that before we treat, whether it's a filtration, a settling step, a skimming step, or something like that, something mechanical, something relatively inexpensive. Then it'll put us back down into that, 2 to 3 cent per barrel range. And I'm going to show you how I got these costs. Now, I did it on the very low end, but you'll get the point of this. Well, also trying to figure out how much is 800 pounds per day. I always struggle with that when talking about oxidants, and that comes from the legacy of how oxidants are treated in all other industries. Essentially, I just go to Google and I type convert 800 pounds per 4.2 million gallons, which is barrels. For some reason, Google doesn't understand barrels very well. But we convert 800 pounds to 4.2 million gallons to milligrams per liter, and that gives me 23 milligrams per liter. Now, if I go the other way around, convert 23 milligrams per liter to pounds per 4.2 million gallons, they'll say you need about 800 pounds of oxidant per day. That's about the best way I figured out how to go back and forth on this. I wish there was an easier way, but that's just how oxidants are generally talked about and how many pounds per day they can generate. And that's why I gave you the treatment rates in the slide before. So there's some other technologies out there. I've dealt with chlorine dioxide before. I've seen the ozones. I've seen that. I'm very pro-oxidant. I think oxidants are a great product in the oil and gas, and I think they can be applied, very well because they get the best kills in the industry. All the oxidants, when applied properly, are very, very, very good at killing bacteria, SRBs, APVs, eliminate H2S, things like that. But it really boils down to, well, what is it going to cost me? And chlorine dioxide, if you're using a 3-chemical process that uses sodium chloride, acid, and bleach on site, the feedstocks can be a little volatile. If a few of you in oil and gas remember a few years ago, we had some HCl supply issues, and essentially that would drive up the HCl. So this can vary some, but if you just flatten out some of the cost, and let's assume you want to generate 3,000 milligrams per liter drum of chlorine dioxide. Now, no one drums it or sells it that way really, per se, but let's say you want to do that. Just in feedstock chemical costs, you're at around $8 to make that drum. To do the same drum of mixed oxidant, you're probably around 85 to 90 cents per drum for 3,000 ppm solution. Now, we don't generate ours that way either, but that's to kind of put it in oil field terms. Now, we do need a little bit more oxidant than chlorine dioxide. We do take a little bit more to treat out H2S, and we do interact with the ammonia in there, but not 9 times more. I mean, you're probably talking 10% more, 20% more, but nothing of any consequence to really impact the cost dramatically versus chlorine dioxide. So it's just a much lower cost solution than chlorine dioxide or even ozone with their power consumption rates. So operating costs per day, how did I go and calculate this stuff? Now, I was conservative on some of the costs, but now you can go back with this slide and actually calculate your own costs based off of how much your salt and power costs. So I assumed we ran at max capacity, 800 pounds per day. We used 3 pounds of salt, and we used 3.5 kilowatt hours. So that's 2,400 pounds of salt and 2,800 kilowatt hours. So if you multiply those out, and let's say we can get salt at 11 cents a pound, I've seen it higher, I've seen it lower, it just depends on what you want to do. And if you truck it in as brine, in Texas and Louisiana, that's extremely cheap to just buy a brine. It can even get lower than that sometimes. And then for power, I've seen as low as 5 cents, I've seen as high as 22 cents in Australia. So this power is probably average for the U.S. And what that equates to is just in OPEX, you're about $500 a day and at 22 milligrams per liter. So that's less than a half a penny per barrel. That's probably not real. You're probably going to need 30, 40 milligrams per liter, but it's still just pennies per barrel to the base operating cost of this. So again, if you actually put all these different costs together and you say 25 cents, 99 cents, 25 cents, 19 cents, 25 cents, there's a lot of room to do the MIOX treatment, add a filtration step, and pay for a tile frac fluid. So to put, this type of cost structure really changes how much you can recycle and how much you can put back into your system. So makeup water required, how much water is required to actually generate the mixed oxidant? In the example I've given you in the slides before, essentially we generate at 4,500 milligrams per liter. So depending on your application, let's say you needed 22 milligrams per liter dosage, for a freshwater, a brackish water, or even a brackish produced blend, then we would need only a 0.5% makeup. So approximately 500 barrels per 100,000 barrels treated. Again, this just needs to be low hardness water. We actually can also use some produced waters as a feedstock. We've proven that up. We have some IP filed around that. And we also can use waste brine streams. So if you have some other process you're doing, whether it's a vapor recompression, a reverse osmosis, or you're doing some kind of process that you have a waste salt stream, just contact us and let us know, and we can run some tests on that and see if that can actually be used as a feedstock to even lower the cost that you'll need to actually generate oxidant. So some of our original pilot scale field trials, so we tested some scale size units in the field before building a full size unit, as we all generally do in the oil and gas. We like to prove things before we spend a whole lot of capital money. And we went through a bunch of different shales and plays and tested a bunch of different water. And I picked out two of the most prominent bacteria counts. So this was a 50-50 produced freshwater blend. So some operators are doing 30, 40, 50% blend. So we figured this was representative of some of the operators. As you can see, 11 million culture forming units per milliliter. That's how much bacteria. So imagine your smallest little perfume bottle that's about 1 milliliter having 11 million bacteria in it. That's a lot of bacteria for any type of industry. We were able to treat that water down to 43 culture forming units per milliliter. Now, one thing to mention here is that with mixed oxidant, we didn't actually get to a residual chlorine number for this particular test. We were only treating at 50 ppm, and the water had a much higher demand than 50 ppm. Though one thing that I've noticed with mixed oxidant versus, let's say, an ozone or a chlorine dioxide is that since the ozones and chlorine dioxides of the world, they're very radical. They want to react very fast with things, and they generally react with the inorganics first. So you have to get to some kind of residual concentration to even get close to achieving these type of kill rates. That's not bad per se, but it just does take a certain amount of oxidant to get to that level. Now with us, we're seeing kill all the way through up even past, up until the point we even get the free available chlorine. Sometimes we don't even get the free available chlorine and we're still seeing great kill, like this example here. So we got down to 43 CFUs per mil. Now that's kind of hard to imagine. So I went to Photoshop and I created a circle, and I took that circle has 11 million culture form, or 11 million pixels is what I did. Now I've scaled this down to fit the slide, but it was 11 million pixels. And then if you look at that dot at the top right by the treated arrow, it actually, and you can't see it very well, but the little white dot that's there, that's 45 bacteria. So essentially this is almost close to zero, even without getting to free available chlorine with mixed oxidant. So I think that's pretty dramatic to show the type of kill that you're getting there. We actually went to the field, and this unit's been running, and it's doing a good job of killing bacteria, but we wanted to prove it on site. And essentially what you're seeing in the picture there is a treated and an untreated pit. So as trucks would offload, half of the water would go to one pit and half would go to the other pit. And so we grabbed samples and made sure that we had chlorine residuals here. And what we did were, you can see the ORP numbers now. You can see there was some ammonia in this water, so we were still reacting with the ammonia in the water, but we were getting extremely good kills. We treated out all the H2S. There wasn't a lot of manganese or iron that we would normally treat out, so this doesn't really show the drop that we would have in those numbers. But essentially what we did is we dropped the bacteria from 10 million to really less than 3 or less than 1 bacteria, because we ran these in triplicate so we could get most probable number. And we've seen this data over and over again, even if we don't get to a free available chlorine number. So we're getting as close to zero as you possibly can get, just like all the oxidants are very good at getting to this number. You just have to dose properly. You don't dose where you generally do with biocides. You want dose where oxidants do best, and that means you have to give them some contact time. You want a few minutes of contact time to actually make sure this water is treated and that the bacteria are completely eliminated. So one of the other things about MIOX is that essentially since all you're using is water, salt, and electricity, and you're generating an oxidant stream that's only 4,500 ppm, you really have a health profile that is very good according to the NFPA. So at worst, if you put your hand in this solution, the worst you'd have to do is actually wash it off. Now it will still bleach your clothes and whatnot, but it's not going to be something that's deadly or dangerous like a 12.5% bleach or a 15% acid or even sodium chloride. Now, this chlorine dioxide number, that's for concentrated chlorine dioxide, but That is a very, it's regulated. You can't ship it. You can't do anything with it, whereas our technology is very safe. It's 100. It's not even classified as an oxidant anymore. So it pretty much cleans up just like as if you were cleaning up water on location. That's why you can actually leave this unit unattended in some applications like a saltwater disposal well or something and really drive down your costs because you don't have to be there to babysit the whole thing the whole time. Now we have some safety features in there. We actually have shutdowns for if it leaks water. We have shutdowns for atmospheric conditions if some type of gas from outside came in or something like that. So there's a lot of safety features in our unit that you can leave it unattended. So in general, just an overview here is that oxidants eliminate the most bacteria in general. They kill better than any of your conventional biocides, your glutes, your quats, your blends, your THPS, and so on and so forth. We can do high treatment rates with a Blackwater unit, or we can even bring out a Gila unit that's larger, and we can recycle more water faster. It's a very high treatment rate. We eliminate H2S. We can reduce iron that causes scale, and we can reduce the chemicals on the road, which is a real plus from a health safety perspective. We're a much safer process, and overall, we're just a lower cost process to help put some of that money from recycling water back into your pocket. And that's the goal of MIOX, is to do that. So I'd like to open it up for questions to myself, and for those real challenging questions, I'm going to revert to Dr. Sue Rivera, but I'd like to open that up now. Thank you. All right, the first question I hear is, can you confirm if your system can be adopted and are modified to produce mixed oxidants from brackish water, around 3,500 milligrams per liter? Oh, this scrolls up when I'm not, okay, which is 80% of sodium chloride and the remaining 20% of sulfates. We've done some tests under 10,000 milligrams per liter that we've seen positive results with, but 3,500 is probably a little low for us to actually generate using that, but we could supplement with salt if we had to. We can definitely supplement with salt to get that oxidant up. An ideal number would probably be in that 20 to 30,000 milligram per liter range. I got a question. What do we do with filtrate effluent from the treated water? We don't filter the water per se. That's another process. We actually have some partners that filter that water. That really depends on what the filtration company would do. We're there to kill the bacteria, treat out the H2S, treat out the iron, and then from there, we're a slipstream dosage. So we're just dosing 20 milligrams per liter into this water from our unit that generates 4,500 milligrams per liter. So I hope that answers that question. Got a question on what's the maximum pH that we can run. I don't know about from the feed water side. I do know our unit produces 9.5 pH oxidant generally. I'm not sure what we can do for the maximum pH coming into the unit. Might have to defer to Susan on that one. Susan, do you know what pH that we require going into the generators?
Usually most waters are coming in at fairly neutral pH, and so I think we can have a fair amount of variability coming in. We can get a better answer though as required.
Yeah, I mean, if you've got a water that isn't in that normal neutral range or something, let us know. We can run tests on that. That's something that can be accomplished. I've got a question saying that they thought our normal moss concentration was about 8,000 ppm. For the Blackwater unit, we've optimized it at the power and salt levels that we wanted at 4,500. We can tweak that up or down depending on the situation. For this one, for maximum efficiency, we chose to generate at 4,500 milligrams per liter. Let's see, another question here. What would I consider low hardness target for your water source? The best ideal world scenario is less than 17 milligrams per liter, I believe that number is, but it really depends on a ratio. We can test a lot higher than that, and we just need to do some preliminary testing to see what that water would do in the cells. Wouldn't you agree with that, Sue?
Yes. Yep.
Okay. All right, I got a question. This one I'm going to divert to you, Sue, is what's the applicability and application method for using MIOX technology to reduce BOD, COD, and or TOC in produced water?
That's a very good question, and it really is dependent on the makeup of your BOD and your COD. Most of the experience we have in this area is from municipal wastewaters, and so we can only extrapolate a certain amount of that type of information for what would happen in a particular oil field scenario. So for most part, a rule of thumb, and it's just a rule of thumb from a municipal wastewater, is that it typically can take it's about a half a milligram of your free available chlorine for one milligram of biological oxidant demand. That's a rough approximation. And so for a particular application, like I was saying, depending on what is causing the biological oxidant demand, there may be some differences. And we run pilot studies and benchtop studies on waters. So if you have a certain application, you can certainly contact Charles and he can route it through to us.
Thank you, Sue. I appreciate that. So I got a question that says, can produced water be used directly as the feedstock or is pretreatment necessary? We have done some lab work on using produced water as a feedstock. It has been successful. I'd be very interested if you have a project to identify on actually running a full-scale project of that. We just need to balance depending on the chlorides of the water, balance how much fresh water we need versus produced water. But it can be done, and there, especially if it's a low hardness water. If it's a high hardness water, then there might be some freshwater dilution involved to get that hardness down to a level that the cells can self-clean themselves. We have technologies where we can actually self-clean the cells, and there's definitely a maintenance cycle that can happen. Depending on the situation, we generally run once a month. We'll do a backwash of the system to clean the anode and cathodes. But we also have some self-cleaning technologies where that's proprietary to us, where we can reverse the polarities and clean it up. So that's it's just depending on the water quality. And if you have a water analysis, I'd say send that to me, and then we can determine the feasibility pretty quickly on whether that can be done or not. So we're getting a question, what is the maximum pH that MIOX can run not to comprise bacterial control, in other words, not be effective? So I'm going to assume they're talking about the hypochlorous acid concentration there. I mean, I know the oil field waters that I've seen, everything in the 6s to the 9s, we've gotten very good kill. We haven't seen any issue with that. Sue, what's your thoughts on that?
Yeah, the field data has corroborated a lot of what we've seen with our lab testing. The only way we can do controlled testing is in the laboratory. And what we see there is that mixed oxidant solution tends to give better kills at the same dose and at the same contact time at higher pHs all the way up to 9.5.
Yeah, and Sue, I think some of that has to do with a lot of times we're actually generating chloramines and trichloramines and things like that, which are, believe it or not, have proven to be a very good biocide for us and very, very effective at killing bacteria.
That's true too.
So, I've got a question on calculating cost per barrel when you include all personnel you need on 24/7 frac location. We can absolutely run those scenarios if that's something we do. We're currently not a service company. We do have some service providers that we partner with to provide that, and their daily charges for personnel vary. It varies dramatically depending on what technology, what other technologies, and how long the contract is. But a cost per barrel, per basis is the manpower is the most expensive part of doing a frac on the fly on location. It is not the equipment. It is not the OpEx. It's actually the manpower. So that's a good question that I can't answer today, but I can definitely get a service partner involved to get you a quote on that if that's what you want. So Sue, we've got a question. Have you looked at COD reduction from compounds such as phenols, and what were the results?
We, to my knowledge, have not looked at those specifically in the field. We haven't done lab studies on those, and so that could be a possibility of something that we could look at. It really would depend on the application and what the treatment goals are. So if you'd like to bring more specifics to Charles, then we could certainly look at it.
Yeah, and that ties into another question that was put up here is who's responsible for me to define a project oil and gas? Is you can send it to me directly. I can be contacted, charles.mowrey, M-O-W-R-E-Y, at MIOX.com. You can go to our website, MIOX.com, and contact us via that way. We also have a great YouTube channel that you can go to and check out some of our videos on our various equipment and processes. This webinar will also be put up there at a later date onto our YouTube channel so that you can send it and talk about it and discuss it and show it to other people if you'd like. So I've got a question, what is the general makeup of your mixed oxidant? And that's where there was some question around this throughout the many years. We've thought it, you know, from MIOX perspective, it's a very difficult thing to determine because in the presence of chlorine, it's very hard to measure any other oxidant species. And what we believe we've narrowed it down to hydrogen peroxide and sodium hypochlorite. We're predominantly sodium hypochlorite, but we do have some percentages of hydrogen peroxide in the oxidant solution is our findings. And we can prove that by doing bacteriological studies and doing bacterial kills so that you can prove we kill more bacteria, more spores, more things than just using standard sodium hypochlorite. If I haven't addressed all your questions, again, contact me directly, charles.mowrey at MIOX.com. We'll go through those questions. I'm going to go through, there'll be a transcript, and I'll go through this and make sure that I didn't miss anything. If I did miss anything, I'll get back to you. And if you have any projects you'd like us to quote, just go ahead and reach out to me and contact me and let me know.